Hello everyone, and welcome back to our series on quantum mechanics. In the previous video, we discussed the intricate linear algebra formalism behind quantum mechanics. In this video, we will finally discuss the famous Schrödinger equation and describe what it represents and how we can use it. Before we can get into the Schrödinger equation, however, we must first define the notion of a Hamiltonian. You might know from classical mechanics that the Hamiltonian describes the total energy of a given system. In our case, we can think of this Hamiltonian as consisting of a kinetic energy term T and a potential energy term V. In the quantum setting, rather than being scalar quantities, of course, we have that all these terms are operators. In classical mechanics, the kinetic energy of a particle can be written in terms of its momentum and mass as follows. As it turns out, this definition generalizes to quantum mechanics accordingly. For the potential energy operator, we simply have that this operator is just equal to the potential energy function V. In general, this potential can be a function of both position and time. However, for our purposes, we only assume that this potential is dependent on position, giving us the following definition. Altogether, we then have that the Hamiltonian operator can be written as follows. Since x and p are Hermitian, we have that t and v, which are well-defined functions of p and x respectively that map real numbers to real numbers, must also be Hermitian. And since the sum of Hermitian operators is Hermitian, we have that h is a Hermitian operator and is therefore an observable. This is of course expected since energy is a quantity that we can measure from classical physics, just like position and momentum. Okay, so we've defined the Hamiltonian as this operator representing the total energy of the system. But what can we actually use it for? Well, this is where Schrödinger's equation comes in. In particular, the time-dependent Schrödinger equation, or TDSE, states that we can relate the time evolution of a given quantum state to the Hamiltonian as follows. I will just write this in the position basis as follows, since this is the basis we will be using most of the time going forward. As we can see, we end up with this second-order partial differential equation. The natural question is how we can actually solve this. Well, we of course need to define our potential energy in order to be able to find solutions to this equation. However, as it turns out, we can make some progress already without even needing to do so. In PDE theory, there exists a method of solving such PDEs using separation of variables, where we assume an ansatz solution consisting of a function dependent on position multiplied by one dependent on time. The goal is to then represent our solution as a linear combination of such products, where the coefficients are determined by the initial and boundary conditions. If we substitute in this ansatz into the TDSE, we can use the fact that the Hamiltonian operator is independent of time to get the following. Rearranging gives us this expression with time on one side and this expression with position on the other. We can set these expressions equal to some value that I will call E, which corresponds to an energy value. We now have two separate ODEs to solve for these time and position components. For the time component, we have the following first-order equation, which we can integrate and rearrange to get what phi of t has to be. Note that here, our choice of integration constant is irrelevant, since this just gets absorbed in the coefficient of the eigenfunction expansion. As we can see, we get this phase factor whose frequency is directly proportional to the energy E. For our function of x, we can rearrange it as follows to get this eigenvalue equation. This is known as the time-independent Schrödinger equation. If we can solve this eigenvalue equation, we can find the allowed energies E sub n of our system, as well as the corresponding eigenstates. Consequently, we have that our wave function is given as this linear combination. You may be wondering how we choose these coefficients C of n. Well, all we simply need is an initial condition. In particular, suppose we know what capital psi is at time t equal to 0 as a function of x. As we can see in our general form for psi, setting t equals to 0 gives us the following linear combination. Since each psi n is orthonormal by the fact that h is Hermitian, we can simply take the inner product with a given energy eigenstate to obtain its corresponding coefficient. Consequently, we can determine how a given state will time evolve under a given Hamiltonian. To gain some intuition on what is happening here, consider the TDSE again. Here, pretend h is just a scalar. You might just recognize that this is simply a first-order ODE in time. If we treat it as such, it turns out that we can actually solve this ODE, and what we get is that the solution simply has the form of e to the minus iht over h bar, operating on psi of x comma 0. Defining this complex exponential operator as u of t, we have that this operator effectively time evolves the state under the Hamiltonian h for time t. Consider the spectral decomposition of H in terms of energy eigenvalues and eigenstates. If we now take the complex exponential of H using Sylvester's formula, we have that u of t is simply given as follows. In other words, this time evolution operator u has exactly the same eigenstates as the Hamiltonian energy, and it simply has eigenvalues given by these phase factors, which are the same as those we calculated in the general form of the state under a given Hamiltonian when it's evolved for a period of time t. In other words, this operator simply scales each energy eigenstate by the given phase factor. Hence, if we can represent any initial state in terms of the energy eigenbasis, and we know the corresponding energies of each eigenstate, we know how the state evolves in time. Since we are only changing each coefficient in the energy basis expansion by a phase, we have that the probabilities of measuring a given energy level remains unchanged as we time evolve the state with respect to a Hamiltonian fixed in time. Additionally, if our initial state is an energy eigenstate, we have that the state actually does not change, since u adds a global phase factor which does not actually change the state. Consequently, these energy eigenstates are also called stationary states. Since the time evolution operator has eigenvalues on the unit circle, and the eigenvectors form a complete basis, we have that this operator is actually unitary. Unitary operators are those for which their conjugate transpose is equal to their inverse. Consequently, if we want to reverse the time evolution for a given state, we simply apply u dagger instead to get the following. Furthermore, unitary operators preserve inner products, meaning that they do not change the norm of a given state. This is essential as we always want to keep the norm of a quantum state as 1, assuming it is bounded, of course. Consequently, any transformation that we apply to a quantum state has to be unitary. We will see some examples of unitary transforms we can apply to our state in the next video, where we introduce the notion of symmetries. Now that we have defined the Schrödinger equations, the last thing I want to talk about in this video is the generalized Ehrenfest theorem. This theorem tells us how the expectation value of a given operator changes with respect to time. The derivation for this is straightforward. Expand the left-hand side as an integral as follows. The middle term simply becomes the expectation of the time derivative of the operator. We can substitute the TDSE for the time derivatives of psi to get the following. Performing some algebraic manipulation gives us the following expression. Some interesting cases to consider here are choosing a equals to x, p, and h. For x and p, we have the following results, which collectively are simply known as Ehrenfest theorem. As you can see, these are actually the same relations that exist between these quantities in classical mechanics. If we now consider a equals h, we find that for time-independent Hamiltonians, the result is 0, meaning that the expected energy of any state always stays the same, which, as we explained before, is expected. This is also consistent with conservation of energy. Altogether, we explored the 1D Schrödinger equation and explained how it can be used to determine how a quantum state evolves over time. In the next video, we will explore how we can use symmetry operations to transform the wave function and determine energy eigenstates more easily. I hope you enjoyed this video, and I will see you next time.